Alright, this video is on section 2.5. We are going to be talking about zeros of polynomial functions. We've been talking about the roots of functions for a little bit now, but now we're going to be including complex roots. So what we discussed in class today, we're going to talk about that a little bit. This is Scotty. He's hula hooping. He's trying to lose a little bit of weight. He's getting fat. Alright. So before we were talking about polynomials of degree n, we said that the polynomial of degree n had at most n roots. Alright, and that was because we were talking about real roots, right? Now, when we introduce the complex roots, we're going to say that every polynomial of degree n has exactly n roots. Alright, so for example, we got f of x is equal to 2x minus 4. Well, this is a polynomial of degree 1. So there must be one root. And if we set this equal to 0, we see that the root is when x is equal to 2. Alright, that's going to be our one root. Here, we have polynomial of degree 2, so there must be two roots. And in fact, then this factors out to be x minus 3, x minus 3. Alright, so there's roots when x is equal to 3 and 3. Although it's the same root, it counts as two roots, alright, because it appears twice. Alright, and we're going to see here, this is where the complex solutions come into play. We have f of x is equal to x to the fourth minus 1. This actually is able to be factored out to be x plus 1 times x minus 1 times x minus I times x plus I. Therefore, we know that there are zeros when x is equal to negative 1, 1, I, and negative I. Alright, it's the fourth degree, so there must be four roots, and there they are. Alright, remember multiplicity. This is kind of what we saw happen right with this one. If I have, for instance, f of x is equal to x squared minus 4x plus 4, this can factor to be x minus 2 times x minus 2. Alright? We're looking for the roots. And that's, as we know, the same thing as x minus 2 squared. Alright? So, this is a degree 2, so there must be two roots, and the two roots are 2 and 2. Alright? And just a little bit of a recap. We know then that because it is a even degree, because this root appears with an even amount of times, it's going to touch it at 2. 1, 2. And it's not going to cross through. Alright? So it's going to look something like that. It's obviously a really rough sketch, but you get the idea. That's just the recap. Alright? Alright, another thing to keep in mind is conjugate pairs. Alright? So if I factor out a function and I'm given x minus I, you know that there will also be a root of x plus I. Every time. Whenever you find a root, the conjugate will always be there. And the reason that is because when we're talking about complex numbers today in class, well, for instance, if we look at this one right here, in this function, there are no i's, right? You don't see any i's there. But there are i's when you factor it out. And the reason you have to always have conjugate pairs is because when I multiply these out, the i's are going to cancel each other out. We're going to have a plus I, we're going to have a minus I, and then we're going to have a minus I squared. And remember that I squared is equal to square root of negative 1 times the square root of negative 1. which is equal to -1. Alright? That's why they come in pairs, because they have to be able to disappear, in a sense. Alright, so say we're asked to find a fourth degree polynomial with zeros at 3, -4, and 3i. Well, just look at this. We know there must be an x minus 3 term for this one. We know there must be an x plus 4 term for this one. We know there must be an x minus 3i term. And, because we know that they come in pairs, we know that there must be a x plus 3i term. Okay? So this function, this polynomial, has zeros at 3, -4, 3i, and -3i. However, as we discussed last week, any polynomial that looks like this will have roots at 3, -4, 3i, and -3i. Okay? So what I mean by this A is I could put, could have put a 3 here, and it's still a valid answer. Alright? This is a fourth degree, and it goes through all those roots. Alright, here's going to be a question that we might see, and it kind of, puts together a few things we've been working on, which is nice. So, find the zeros of f of x is equal to x cubed minus 3x squared plus 25x minus 75, given there is a 0 at 3. Well, if we know there's a 0 at 3, that means that there must be an x minus 3 term within there, right? Well, if there is an x minus 3 term in there, that means we can divide that x minus 3 term out and see what happens. So I'm going to use my polynomial division that you guys all are such big fans of. And I'm dividing out x minus 3. Alright, we need x squared here, the first one. So it's going to give us x cubed minus 3x squared. That's 0 minus 0, and I'm going to pull down the 25x. Pull that down. I'm going to multiply it by 25. It's going to give us 25x minus 75. And you see if I pull down that, it's going to give us 0 as well. So there's no remainder. So that means that this times that is equal to this. Alright? So if I just go over here, I can see that f of x is also equal to x minus 3 times x squared plus 25. Alright, well, there's our roots at 3. That means our other roots must be in this piece. So if I set x squared plus 25 equals 0, well, I get x squared is equal to negative 25. And we know then we're going to have a negative square root, so we're going to have some complex solutions. And in fact, it's going to be 5i and negative 5i. So, going back over here now, well, this is going to be factored out to be x minus 3, x plus 5i times x minus 5i. Okay? Alright, so that's kind of good. I mean, we got to use the information we're given that there's 0 at 3 to know that there's this term within there. Divide it out. Find that there's no remainder, so then we are left with this bit right here. We can use that to find our other two roots. And since it's a third degree polynomial, we know there must be 3 zeros. We're given 1. We found the other 2. Alright? Okay, here are your questions. There's only 2 of them. Pretty straightforward ones, so have a blast.